So today we're going to be talking about concavity in section 3.4. My plan for tomorrow, well, I know I won't see you guys tomorrow, but I'll see you for 2 hours on Friday. So we will, what we'll do is we'll have 3.5 notes, followed by a homework assignment, and then also an assignment that sort of puts everything together from 3.1, 3.3, and 3.4. So that will be the plan for Friday. But for today, we're talking about concavity. Now, if you look at the graph on your guided notes, the first piece of your graph is considered what we call concave down. So if we trace up to that point, which I've labeled an inflection point, that's considered concave down. And I think the easiest way to think of it is to think about like a parabola. If a parabola opens down, it's concave down. If it opens up, it's concave up. Now, it doesn't have to be a parabola, obviously. This graph is actually, looks like a trig graph. Looks like the graph of maybe sine or cosine. But if you just think about the orientation of a parabola, I think that helps you understand the difference between concave up and concave down. So this piece here, which I'm going to outline in red, this piece of the graph is what we consider concave up. So in 3.1, remember we talked about absolute extrema. Then in 3.3 we talked about relative extrema. And now in 3.4 we're talking about concavity of a graph. So the idea is by the end of this chapter, you'll be able to use calculus to identify very important characteristics of really any function using your calculus, and then you can come up with a very accurate sketch of the graph without using a calculator, just solely using calculus. Under here where it says the graph of f is concave upward if, I want you to write f double prime is positive, which means it's greater than 0. The graph of f is concave down if f double prime is negative, or simply less than 0. So what we're doing today is very similar to what we were doing yesterday. If you remember, yesterday we learned the first derivative test for finding relative extrema. So we had to set the first derivative equal to 0, find the critical numbers, we set up intervals and created this big chart, and we tested in the first derivative. If the first derivative were positive, that meant that the original function was increasing. If the first derivative was negative, that meant the original function was decreasing. And then if it changed from increasing to decreasing, we knew we had a relative max. Or from decreasing to increasing, we had a relative min. Well, today is very similar to what we were doing yesterday, but instead of using the first derivative, we're using the second derivative to test for concavity. So if you look at the bottom of your guided notes, it says, determine the open intervals on which the graph of f of x is concave upward and concave downward. And I went ahead and just typed the steps onto your guided notes there, but let's talk about each one real quickly. We'll just skim over it, and then we'll actually work through this example together. So the first thing that you do is you find the zeros of the second derivative, and any numbers where f double prime does not exist. Then you're going to divide the number line using those numbers. Again, very similar to what we were doing yesterday, but yesterday we were using the first derivative and today we're using the second derivative. The third step is to test a value within each of those intervals. Test it into the second derivative. And then number 4 is decide if the graph is concave up or concave down on each interval. All right, so let's do that for number 1. The graph that, or the function that we're starting with today is x to the 4th minus 4x cubed. So the first thing you have to do is find the zeros of the second derivative. The second derivative. So let's find the first derivative. Evan, can you help me out with the first derivative on number 1?
Is it 4x cubed?
4x cubed, good. And then minus, what's the derivative of 4x cubed? 12x squared, okay, so that's the first derivative. Now we need the second derivative. Jason, what's the second derivative of f of x?
12x squared minus 24x.
12x squared minus 24x, great. And so after you find the second derivative, you're going to set the second derivative equal to 0. So 12x squared minus 24x equals 0. Now notice the second derivative is quadratic, and we learned several ways for solving a quadratic in Algebra 2. But I think in this case, probably factoring will be the easiest, fastest way to solve for x. So we're just going to factor out the GCF, which happens to be what? Good. So pull out a 12x, and you're left with x minus 2. Good. And then we're going to set each factor equal to 0 and solve for x. So x equals 0 and x equals 2 are my two zeros of the second derivative. Now after you find the zeros of the second derivative, remember you're going to divide your number line just like we did yesterday and set up test intervals. So if you need to draw the number line, you certainly are welcome to. And so if we have 2 zeros of the second derivative, we need 3 test intervals using this number line as a guide and reading it from left to right. Remember, negative infinities on this end, positive infinity on the right hand side. So if I divide this into 3 intervals, Hannah, can you tell me the first interval I would use? Good, and I'm just going to move it over here a little bit so I have more room to work. Negative infinity to 0 is my first interval. Allison, can you help me with the second interval, please? 0 to 2, great. And, excuse me for just one moment. Ms. Gray? I do. Okay. All right. Renee, they want to see you in the cube with Miss Ellis. Okay. All right, so negative infinity to 0, 0 to 2, and then our last interval, Cole, what would that be?
2 to positive infinity.
2 to positive infinity, great. So now I've divided my intervals, and this time I'm going to test into the second derivative. Remember yesterday we were testing in the first derivative? Everything today is the same process, but instead of using the first derivative, we're using the second derivative. So I'm going to do f double prime of any number between negative infinity and 0. I'm going to pick negative 1. You may choose whatever number you like. And then I'm going to pick positive 1 in the second interval. And I'm going to pick 3 in the third interval. And remember, we don't really care what the actual answer is. All we care about is if it's positive or negative. So if we put negative 1 into the second derivative here, we have 12 times 1 minus the negative 24, so plus 24. So is that going to be positive or negative? That's going to be positive. If we put 1 in for x into the second derivative, we get 12 minus 24, which is negative. And if we put 3 in there, 12 times 3 squared minus 24 times 3. 12 times 9 minus 24 times 3, is that positive or negative? Positive. That's going to be positive as well. Now, again, I want to just reiterate, like I said yesterday, it's not, don't always assume it's going to alternate plus minus plus or minus plus minus. you do need to check every time, because sometimes you might have plus minus minus or minus minus plus. That's definitely a possibility, so make sure you test each interval. And so what that tells me is that my graph is concave up from negative infinity to 0. It's concave down from 0 to 2, and then it's concave up again from 2 to infinity. And so if I want to write that using correct notation, I would say concave up from negative infinity to 0, union 2 to positive infinity. And then I'm going to say concave down from 0 to 2. Now, if you look back up at the graph we started with, I mentioned the fact that I had labeled a point an inflection point. That's probably a new term for most of us. Basically, the inflection point is where a graph changes from concave up to concave down. So anytime the graph changes concavity, as long as the function exists at that particular x value, that x value is considered an inflection point. So with the first derivative test, we had to distinguish whether it was a relative min or a relative max when it changed from plus to minus or minus to plus. With concavity, as long as it changes signs and the x value actually exists in the original function, there is an inflection point there. So this graph contains two inflection points, okay? It has an inflection point at 0, where it changes from concave up to concave down. And it has another inflection point at 2, where it changes from concave down to concave up. So I'm going to try to squeeze that in here, that we have an inflection point, sometimes called a point of inflection. But we have inflection points at 0 blank and at 2 blank. I want you to list the ordered pairs for me. So do you remember from yesterday, once we figured out the x value, how did you find the y? Yeah, we plug it back into the original function this time. So if you will put 0 back into the original function, so I'm going to take 0 and I'm going to sub it back into x to the 4th minus 4x cubed. I get 0 again. And then what if we put 2 in for the original function? 2 to the 4th minus 4 times 2 cubed. What is that? 16 minus 4 times 8, so 16, yeah, negative 16, good. So we have inflection points at 0, 0 and at 2, negative 16. Now, what I like to do after we've actually analyzed the function is I like to graph it just to see that my calculus is correct and it holds up. So when we were doing, yesterday when we were doing relative extrema and then we got our calculators out to look at the graph, that was just to check our work. Okay, so the calculator is, for these problems, really only to be used to check that your calculus is making sense graphically. So if I type in my function, x to the 4th minus 4x cubed, I'm typing in the original function. So x to the 4th minus 4x cubed. And then I'm going to start out in the standard window. Looks like I may have to adjust my y minimum just a touch. And I'm even going to zoom in, I think, on my x's. So I'm going to go to my window, and I think I'm going to say negative 5 to positive 5 on the x values. And then I'm going to change my y minimum to negative 20 on a scale of 2. Okay, so when I hit graph, looks like I need to go a little bit lower than negative 20. So I'm going to go window, let's try negative 30 and see if that gets it. Perfect. Okay, so I'm just testing or checking to see that my concavity test actually works. So my claim is that this graph is concave up from negative infinity to 0. So from negative infinity to 0, it's concave up. And it actually almost looks like half of a parabola, doesn't it? And then it changes at 0 to be concave down. And it's concave down, we say, until we get to about 2. So we're saying the inflection point happens right here, right around here is where the inflection point happens. And then it changes to concave up to infinity. Isn't that cool? It's awesome, right? We did all that using calculus, and then we got to verify it using our graph. Well, yes, you may. Okay, let's flip over to the next page. So the back of your page, number 2, I'm actually going to start my number 2 a little bit higher because I'm going to need some more room. Just a warning, you may want to kind of write small on this one because we're going to need a lot of room to get that second derivative. So I'm going to start all the way up here in my top left-hand corner. And so my function was f of x equals x squared plus 1 over x squared minus 4. So what do we need to do to find the derivative here? Yeah, we need the quotient rule. And so that's going to give us our first derivative. So for our quotient rule, we have low d high minus the high times d low all over low low. And then we can simplify that a bit. Let's go ahead, save us some writing, and let's distribute the 2x to the first parenthesis, and we get 2x cubed minus 8x. And then I'm going to distribute the negative and the 2x to the parenthesis containing x squared plus 1. I'm going to do that all in one step. And I get negative 2x cubed minus 2x. And now when I combine like terms, that's going to give me negative 10x on top. And then in the denominator, I have x squared minus 4 squared still. That is my first derivative. Now, how do I find my second derivative? I gotta do quotient rule again, that's right. So quotient rule again for the second derivative. So f double prime of x is going to look like low d high. So x squared minus 4 squared, d high is just negative 10, minus high d low. What do I need for d low? Yeah, I need chain rule, don't I? So I need 2 times x squared minus 4 times 2x. We got to chain on g prime to the end. All over. Low is just going to be x squared minus 4 squared all squared. So essentially it's just x squared minus 4 to the 4th power. And you can go ahead and write that if you want to. I'm showing that step here, but you can certainly go ahead and write it. All right, now, instead of multiplying everything together here, What I want you to do is to use that little technique that we've been using when we have used the product rule before of factoring out the GCF from the numerator. And hopefully you'll see why I'm doing that here in just a second. But we have two terms. I'm going to circle them for you so that you can see the two terms. And then I want you to look at those two terms and decide what the GCF would be for those two terms. Okay, x squared minus 4 is part of it. And then the negative 10 also, right? So let's pull a negative 10 out. And let's pull an x squared minus 4 out. And then let's see what's left inside parentheses. What would be left inside this first circle? Just x squared minus 4. And then I'm going to say minus whatever's left inside of this second circle. Well, the negative 10's gone. So the x is still there, the 2 is still there, and the 2x is still there. So multiply those all together for me. 4x squared. And then I have x squared minus 4 to the 4th. Can you see why I did it that way instead of multiplying everything all together?
Yeah.
What happens in this next step? Yeah, you can actually divide out an x squared minus 4 and simplify. If you multiplied everything together and then combined like terms, you'll probably miss that cancellation because everything will be multiplied together. So that's why I had you factor out the GCF. But I can factor out an x squared or cancel out an x squared minus 4. That will leave me with an x squared minus 4 cubed on the bottom. And so negative 10 times the quantity negative 3x squared minus 4 all over x squared minus 4 cubed. Shoo, that was a lot. That is my second derivative. Now I need to find the zeros of that second derivative. Do you remember the little hint or tip I gave you whenever your derivative is a fraction? There you go. Numerator and denominator have to be set equal to 0 separately. So I'm going to set negative 10 times negative 3x squared minus 4 equal to 0. But I'm also going to set x squared minus 4 cubed equal to 0. And I'm going to solve each one of those. Well, over here, if we divide both sides by negative 10, and then move the 4 over, we get x squared equals negative 4/3. I know I did that rather quickly, but I'm just getting x squared by itself. And once I've got x squared by itself, then, excuse me, I take the square root of both sides. And do you remember what I told you yesterday if you get a negative under the square root? Yeah, then it doesn't exist because that creates imaginary numbers, right, when you have a negative under the square root. So if you have a negative under the square root, then we don't have any zeros from the numerator. That just means that there's no x-intercepts since the numerator never equals 0. And then over here, if we take the cube root of both sides, I get x squared minus 4 equals 0. Remember, I don't do plus or minus 0. Number 1, it wouldn't matter because positive and negative 0 are the same. But number 2, it's an odd root. You don't do plus or minus with odd roots. But you do plus or minus with even roots, which will help us out in the next step. So x equals plus or minus 2. All right, so those are the two numbers that I'm going to use to create my intervals. So can you create the intervals without drawing the number line at this point, you think?
Yeah.
What's our first interval?
Negative infinity.
Okay, negative infinity to negative 2. And then second interval? Negative 2 to positive 2. And one more. 2 2 to positive infinity. So I'm going to create my chart, and then I'm going to test where? I'm going to test into the second derivative, because this is for concavity. If I'm testing for increasing or decreasing in relative extrema, I use first derivative. If I'm testing for concavity, I do the same exact process, but I use the second derivative instead. So I'm doing f double prime of -3. I'm doing f double prime of 0 and f double prime of +3. And all I care about is if those will be positive or negative. So here is my f double prime. If I put -3 in there, let's see what we get. If you put -3, you're going to get +9 on the top. So -27 minus 4, that's going to be negative. Negative times negative makes a positive on top. If I put -3 in the bottom, I get 9 minus 4, which is a +5 cubed, which is a positive. So we said we had a positive on top and a positive on bottom. Positive divided by positive is positive. Again, we don't really care what the number is. We only care if it's positive or negative. What about 0? On top we have a negative times a negative, which makes it positive. On the bottom we have -4 cubed, which will be negative. Positive divided by negative is negative. And then if we put +3 in there, well, if you think about it, +3 is going to give us the same answer as -3, because when you sub in for x, you square it, and they both give you +9 when you square it. So without even thinking about it, we should be able to say that's going to be a positive. So that tells me I am concave what? Concave up, concave down, and then concave up again. Now be careful when you start talking about inflection points. Let's write out our concavity first. So I'm going to say concave up from -infinity to -2, union 2 to infinity, and concave down from -2 to +2. Now, based on the last example, you might assume that we have inflection points at -2 and at +2, because it does change concavity there. But look what happens when you try to sub in -2 and +2 back into the original. What's going to happen when you put -2 and +2 back into the original equation?
You're going to get 0 in the denominator.
You get 0 in the denominator, which means the function doesn't exist at -2 and +2. Okay, so I mentioned inflection points happen whenever concavity changes, but the function actually has to exist at those x values. Now, you would have figured that out, because when you went to figure out the y value, you would have seen there's a 0 in the denominator. But I want you to make a note at the bottom that there are no inflection points. No inflection points. No points of inflection. And the reason is, where it changes concavity, the function doesn't actually exist. And if I bring my calculator up here, I'll show you what's going on at -2 and +2. So I'm just typing in x squared plus 1 over x squared minus 4. Notice I'm using my TI-84 today. It's just more user-friendly, I think, especially when you're typing in functions like this. You can type it in as fractions and not have to worry about all the parentheses. But you're welcome to use either one, 84 or an 89. So now when I go back to my standard window, zoom 6, see what's happening at 2 and -2? I have asymptotes there. So the function doesn't exist there, but it still changes concavity there, doesn't it? Because I have concave up, even though it doesn't look like a parabola this time. Can you all see the concave up from negative infinity to 2, concave down from negative 2 to positive 2, and then it's concave up again from 2 to positive infinity, which is what we found using our calculus. All right, any questions on the concavity test? So the concavity test works exactly like the first derivative test, but we use the second derivative, okay? Kind of bothers me a little bit that it's not called the second derivative test, but that's what we're going to do next, is the second derivative test. The second derivative test is an alternative way of finding relative extrema. So if you look on the right-hand side of your guided notes, I've made a note there that the second derivative test is actually used to find relative extrema. That's what we did yesterday, was the first derivative test to find relative extrema. This is just a different test that will solve for the relative extrema like we did yesterday. All right, so here's how it works. Number one is to evaluate f prime at the zeros, or evaluate f double prime at the zeros of f prime. Excuse me. If f double prime is positive, you have a relative min. It's kind of opposite of what your instincts tell you to do. Positive means a minimum. And if f double prime is negative, you have a relative max. Now, if f double prime equals 0, the test fails and you have to do the first derivative test anyway. I normally just use the first derivative test because that is the test that always works. This test, however, some people think it is easier and faster, but it doesn't always work. That's the problem with this test. I have seen a couple of questions on former AP Calculus exams where you were forced to use the second derivative test. So it's not that you shouldn't learn how to do it if you know how to do the first derivative test. It's important, I should say, to know both the first and the second derivative test. First derivative test to me is more powerful because it always works. But the second derivative test is also used for finding relative extrema. So let's just go through an example and let you guys be the judge. Which one you think is easier? So step one says evaluate f double prime at the zeros of f prime. So the first thing we need to do is find f prime and f double prime. So Angel, can you tell me f prime for number 3? 5x to the 4th minus 5. Okay, good. And so then f double prime, excuse me, Kaylee, can you help me with f double prime?
20x cubed.
Good, 20x cubed. So I found f prime and f double prime. Now it wants me to evaluate f prime at the zero, or f double prime at the zeros of f prime. So to find the zeros of f prime, you simply set it equal to 0 and solve it for x. So I'm getting x by itself. I moved the 5 over, divided both sides by 5. Now I need to take the 4th root of both sides. And since it is an even root, we have to make sure to do the positive and the negative root, plus or minus 1. So those are my zeros of f prime. Step 1 tells me to evaluate f double prime at those zeros. So I'm going to take f double prime and sub in negative 1, and I'm going to substitute in positive 1. All right, if we sub in negative 1, again, all I care about is if it's positive or negative. If I put negative 1 in there, do I get a positive or a negative number? I get a negative. If I put positive 1 in there, what do I get? Positive. So that means I have a relative, negative means max. Remember I said it's opposite of what your instincts tell you. Negative means relative max at -1 something, and a relative min at +1 something. How do we find the y values?
Original.
Got to sub back into the original equation. So if I put -1 in there, into the original equation, I get -1 plus 5 plus 3, 7. What if I put +1 in there? 1 minus 5 plus 3, -1. So we're saying we have a relative max at -1, 7 and a relative min at 1, -1. Let's check it out graphically and see if that's true. So I'm just typing in x to the 5th minus 5x plus 3 into the standard window. So I'm going to go zoom 6 if I'm using an 84. If I'm using 89, I go F2 6. Alright, on the 84, to check your maximum, you're going to go to second trace, number 4. On the 89, I think it's F5, and then choose maximum. It's the math menu on the 89, if you guys are using the 89. Left bound and right bound, -1, 7 for the max. Is that what we found? Yeah, -1, 7 is our maximum. And let's try our minimum. I'm going to go to second trace, left bound and right bound. And I got +1, -1, which is what we came up with for our relative minimum. So you can be the judge which test you like, the one we learned yesterday or this one. Some people just think this one's easier and faster. But again, if when you sub in F double prime you get 0, remember 0 is neither positive nor negative. So this test fails and you have to go back and do the first derivative test anyway, if you get 0 when subbing into F double prime. Okay? But this is called the second derivative test. Then the test that we learned at the beginning of class today, I just call that the concavity test. You're using the second derivative, but I call it the concavity test. All right, let's try number 4. Let's see if we have time to get number 4 in. So we're still just trying to find the relative extrema. So we're going to start with f prime. It's -15x to the 4th plus 15x squared. And then f double prime would be -60x cubed plus 30x. Everybody with me so far? Find the first and the second derivative. Then I need to find the zeros of the first derivative and sub them into the second derivative. Now,